In this video, we're going to take a closer look at the question, what is mass? I don't claim to have all the answers, but there are two things I think are important to have clear. The first is that the idea of inertial mass is problematic at a conceptual level. Resistance to acceleration is a Newtonian concept and does not quite work in all settings. In fact, it's not really used in relativity or particle physics, and we'll see why. Second, as a consequence, I want to offer a different intuition which I think works better. In a nutshell, more massive bodies have more states within the same range of speed. We need to understand what that means precisely, but I think this maps better to how rest mass is used in special relativity, particle physics, and all other fields. But let's not jump ahead too much. Let's start with Newtonian mechanics. Inertial mass measures how hard it is to accelerate an object. We have a trajectory, the velocity at each point, and the accelerator. The idea comes from Newton's second law that tells us that force is mass times acceleration. So if the force is kept the same, lower mass means higher acceleration. Therefore, a smaller mass is easier to accelerate than a bigger mass, and this is the basic intuition. Now let's put that intuition to the test. If a smaller mass is easier to accelerate, we would expect that a body with zero mass would be extremely easy to accelerate. An object with infinite mass, instead, would be impossible to accelerate. What we actually have is that a body with zero mass, for example, a photon of light, is impossible to accelerate because it always goes at the same speed, the speed of light. So a body with zero mass seems to work more like a body with infinite mass. This intuition, low mass, easier to accelerate, betrays us here, and good intuition should never fail us. Another issue is that inertial mass is not invariant. It does not look the same to all observers. If you study special relativity, you know that the relativistic mass is gamma times the rest mass, where the gamma is a function of the speed. The faster something goes, the harder it is to accelerate it. You may think at this point, well, all these problems are just really with relativity, so let's think about a case in Newtonian mechanics. You have two observers, both with their own definition of time, their own clock. They may have different jitter, one may go faster than the other, yet we should be able to write one time as an invertible function of the other. So t hat is a function of t. Let's write the second law for the observer using t hat in the form of change of kinetic momentum instead of mass times acceleration. F hat is the force as measured by the hat observer, and m hat is the mass he sees. Now, using the chain rule, we rewrite the derivatives in terms of t. dt hat is the difference due to the clocks. Note that the new expression is almost the force for the second observer, except for this dt hat. So we put it on the other side. We have that the force for the second observer is dt hat dt times the force of the first observer. This is equal to the derivative of time of m hat dt hat times velocity. So m hat dt hat is the mass as seen by the second observer. The mass perceived by the second observer is different. Worse, in general, dt hat may actually change in time, so the mass may not even be perceived to be constant. The point is that redefinition of time implies a redefinition of mass even in Newtonian mechanics. And this is not something else. It's the same effect we have in relativity. In fact, in relativity, the time t of a moving observer is slower than the time at rest, t hat, by exactly a factor gamma. That's the same transformation law with the same meaning. Relativity just exposes it because there is no absolute time. So we have to bite the bullet. Inertial mass is not a fundamental concept in the sense that it is not always applicable in the same way to all problems. It should not be our cornerstone for a physics understanding. Now, don't get me wrong, it's a tremendous useful concept in all sorts of physics and engineering situations. I'm not saying you shouldn't use it, just be aware of the goal. If you want to promote general fundamental understanding of the physics laws, well, inertial mass is not going to cut it. In fact, in many areas of physics, inertial mass and relativistic mass are simply not used. You use invariant mass or rest mass. So what does that really represent? To understand that, let's take a detour. There are two fundamental things we want to capture in physics. One is the dynamics of the system, the states and their evolution. The second is the kinematics, the trajectories in space. The first is better described in terms of position and momentum. It's about the causes of motion, the energy, and so on. The second is described by position and velocity. A quick side note, I use q for position as a state variable and x as a position as a kinematic variable. There is a reason for that. It makes derivatives more clear. I'll explain that in another video. Here, q and x are basically the same thing. Going back to our discussion, one other thing we want to be able to do is count the states within a region. Position and momentum are such that dq dp directly counts the number of states within an infinitesimal region. Essentially, you have a unitary density of states over the state variables. That is why Q and P are special and you want to do statistical mechanics in phase space. But here's the thing. You may want to count states using ranges of kinematic variables instead. dq and dx are the same, as we said, they're both position. dp instead is mg dv. This g here is the metric tensor. It's a matrix that is calculating the scalar product between dx and dv. So you see, m is the constant of proportionality between the two expressions. For the mathematically inclined who studied measure theory, the counting of states is through a measure, and the mass relates the measures of the states to the measure of the initial conditions. It relates the measure on the two spaces. By more states, I do not mean mathematical cardinality of the set. How many points are there? Any area will have infinitely many points. Set cardinality is rarely important in physics. The set of points in 1 meters has the same cardinality than the set of points in 1,000 meters. It's always that of the continuum. But 1,000 meters has more space than meters. This more is a measure theoretic more. So regions of space have more or less states in the same sense. You may ask, why do we care? Because knowing how to count states means being able to say whether the dynamics is deterministic and reversible. If the evolution concentrate, we map more states to fewer states, then the dynamic is dissipative. If we map states 1 to 1, we have deterministic and reversible evolution. The number of states is preserved. So the ability to give a size to the sets of states is a fundamental requirement for a state space. Mass allows us to carry those sizes to regions of initial conditions, on sets of possible trajectories. The mass then measures the density of states per unit of speed. It tells us how the modulus of p changes if the modulus of v changes. For example, if we have the same velocity interval from v0 to v1, then the more massive body will have more states within the same interval than the less massive body. So why is a more massive body more difficult to accelerate? Because for the same change in speed, it has to go through more states. The force will quantify the change by counting the number of states changed per unit time. Note that gravity acts directly on the velocity, makes the same change of velocity for all bodies, so it will push harder the more massive bodies because it will need to make them go through more states. So more massive bodies are heavier. If the speed is the same for all states, then the modulus of v does not depend on the modulus of p, and vice versa. So the mass, the derivative of mod v over mod p, is 0. But also the derivative of mod p over mod v is 0. This is why zero mass kind of works as infinite inertial mass as well. If mod v is independent from mod p, then mod p is also independent from mod v. So why can't we accelerate massless particles? Because you literally have no states within almost all range of velocity. You have no states to change to. So what have we learned? Inertial mass is really a Newtonian concept. It's not general, it does not always work, it's not invariant under time redefinition. The intuition we build on top of it does not go very far. Being able to count states, on the other hand, is something that is fundamental. In particular, characterizing how states are counting over kinematic variables over initial condition is fundamental, and the mass tells us how many states are there per unit speed. That's how I like to think about it. Note that I still do not know why this would be linked to gravity, why the mass of one body should influence the trajectory of the others. But, one step at a time.